Okay, lesson two, relationships between two quantities. Go ahead and pause the video right now and just read through this first little bit here and see if that makes sense to you. Okay, list one more example of a relation. Well, I got one I'm thinking of might be the number of car accidents is related to maybe your age. So the younger you are, the younger the driver is, the more accidents he's likely to have. Okay. All right. Again, my goal here is to keep these videos short, but there is a lot of text and a lot of reading and a lot of definitions in these first few lessons. So I will require everybody to go through and read this very carefully when we start doing this. Okay, so go ahead and read through the different ways of representing a relationship, and I'm going to jump right down here to looking at an example in the investigating a relationship part. Okay, before I get into it, I want everybody to go ahead and read this whole section. This is a very important piece here. There's a lot of important concepts to go over. So go ahead and read it, and then I'm going to try and go over each one. Okay, the relation is the cost of driving a car and the speed at which you drive the car. The variable used for the cost is C, and the units are cents per kilometer. And S is used for speed, and that the units are kilometers per hour. Okay, so there is some relationship. Okay, we all know that if you got in a car and stepped on the gas and drove at 150 kilometers an hour, you would waste gas a lot faster than if you drove it at 80 kilometers an hour. Okay, that's known. All right, there's a relationship there. And as a matter of fact, the speed limits. One of the reasons that speed limits were introduced wasn't to save lives and make people drive slower. It was actually to save money and to save fuel, because in the 70s in North America the price of gas was very expensive. So the governments put in these laws where you had to speed limits where you had to drive at a slower than 80, slower than 60, and that was more to do with speed limits, saving money on gas than saving lives due to speed. Okay, so the first concept that we get into is the idea of dependent variable versus independent variable. Okay, and in this case, the cost of driving the car is the dependent variable, and the speed is the independent variable. Okay, and the way we look at this, you might ask, why is this the case? Well, the cost depends upon the speed that you drive the car, and hence the cost is the dependent variable. Okay, the price does not influence the speed. It's the other way around. The speed influences the price. That's kind of how you want to think about dependent and independent variables. Okay, the other concept is input and output. Well, input and output, independent variables are the input, and the dependent variables are the output. So the way this would work is, if I want to input a certain speed, and the input is just like saying, okay, what if I drove 80 kilometers an hour? And the output would be the cost, the cost of driving at that speed. Okay, so the input would be the speed, the independent variable, the input would be speed, and then the output would be the cost. Okay, the last concept is this concept of domain and range, and that's also very important. All the possible values that make up the domain are the independent variable. So if our independent variable is speed, okay, all the domain would be maybe something from, well, it would go from 0 kilometers an hour all the way to, as fast as you can drive your car. It might be 200 kilometers an hour. Okay, that would be the domain. So it's all the values that you can possibly have for your independent variable. Okay, the range, on the other hand, is the cost cost, all the possible values for the cost. Well, if you turn the car off and don't drive it, well, there's no price, you're not wasting any gas, so the cost is zero. And then it might go all the way to, if you drive at 200 kilometers an hour, well, you might be paying the most money. And again, it's cents per kilometer, so you might be paying, something like 40 cents per kilometer. So that's cents per kilometer. Okay. Again, that all depends upon how fast you're driving. Okay, go ahead and read through this little part here, and then we're going to look at all the possible ways we can show this relationship between cost and speed. Okay, so again, the input is speed. Here's a table of values. We've all seen this. So the way we read this is if speed is, again, this is kilometers per hour, and this is cents. Okay, cents. So if I drive at 20 kilometers an hour, it costs me 10 cents. If I drive at 30 kilometers an hour, it costs me 9.1 cents, and so on. Okay, you can see that the cheapest, the best speed, the one I'll save the most money is over here, and that's 70 kilometers an hour. The cost is 7.5. Okay, you can write these as ordered pairs, like as if you were to graph them. So this would be the x and the y variables. Okay, in this case, the independent always goes in the x-axis, and the dependent always goes in the y-axis. Don't worry about the mapping one for now. Okay, we'll ignore that one. And then of course you can do this with a diagram where the speed is on the x-axis and the cost is on the y-axis. And again, what we see here is, if we're driving 20 kilometers an hour, okay, 20 kilometers an hour, that's all the way, that's cost me 10 cents right there. That's that point. So this would be the 20, 10 coordinate. This would be the 30, 9.1 coordinate, 48.4, and so on and so forth. Okay, you can see this here would be the cheapest, and that would be that 70 kilometers an hour, 7.5 cents. Okay, so if I was driving on a highway and I want to save some money, I'd probably want to drive at 70 kilometers an hour. I certainly don't want to go above 120, and that would cost a lot of money. So there's several different ways of representing this relationship. Okay, go ahead and read through this section over here, and notice this this input here. So first of all, pause the video and read through this little sentence here, and then now I'm going to talk about this doesn't make sense if I put speed as 5,000, because that would be somewhere way over here, right, off the page, and that would make sense because the car can't really go that fast. Okay, now the last way to, and probably the most important way to represent this relationship is with an equation. And here's the equation. Okay, now this is, I'm not asking you to come up with this equation. Most of the time they're gonna give it to you. This is a pretty hard one, and you'll be able to do these curved equations, which are called parabolas, in grade 11. But you still need to understand what's happening here. And here's the equation. Okay, so the equation is, and again, this is the cost. So cost equals 0.001. And then it's going to be speed squared minus 0.14 times the speed, and then finally plus 12.4. Okay, so you can pick any speed and input it into the equation here. Again, this is why we call this variable the input, the independent variable. I can input, let's say, 43 kilometers an hour, and I'm going to get the output as the cost. Okay. All right, so and we talked so go ahead and read this, and I already talked a little bit about this, but the point here is that the independent variable goes in the x-axis and the dependent variable goes on the y-axis. So go ahead and read this on your own, and I'm going to move on to the next little section here. Okay, so let's do a few examples now. I have State the independent variable. Okay, well, the independent, again, let's ignore this for now. I have here V and A. I don't really know what those are, but it doesn't matter because I know that the first one is going to be the independent and this is going to be the dependent. Okay, the independent one is always written first. Okay, all the inputs, list all the inputs. Well, the inputs are 4, 10, and 25. State the dependent variable. Well, this is the A is the dependent variable. List the outputs, so that those are the inputs. Okay, right there, and then the outputs are 15 corresponds to the 4, 12, and 15. Okay. Over here, all the inputs would be all the all the x coordinates would be, so it would be B. Inputs would be B, comma 3, comma 4, comma 5, and 6, and the outputs would be C, 7, 11, 15, and 19. Actually, the B and the C don't go in here. They're just telling us what those are called. Okay, and again, that would be the B, and that would be the little C here. So again, this I don't really know what those correspond to, but again, it doesn't really matter as long as we have the variables there and we understand which one is the input and which one is the output. Okay, again, this would be the independent, and this would be the dependent. I'm just going to put a big D there. Okay, let's do another example here. The diagram shows relations expressed in a different way. In each case, state the independent variable. Well, we all know this one. This is the circumference equals 2 times pi times the radius. Well, the radius in this case is the independent variable because the circumference in this case depends upon the radius. Okay, sometimes it's not so obvious, and sometimes it can work both ways. Okay, if we rewrote this equation and isolated the r, the radius, I could write this as radius equals circumference divided by 2 pi, and now the circumference would be the independent variable. In most cases, it does matter which one can be the independent and dependent. However, sometimes, like in this case, both of the variables can take on both of the roles, depending on which perspective you're looking from. All right, look at this one. State the dependent. Well, this one is time. Time is usually the independent variable, and the height is the dependent. Here's a way of looking at it. Dependent, okay, because this is somebody's height as they're growing into adulthood. Or it doesn't have to be. It could be a plant, okay, a plant growing. So this is, when the plant was, right here is when the plant was planted, okay, and it was, this might be 5 inches, it might be 5 meters, I don't know what it is. But, when it was first planted, it was small, and then it grew as time went on, and it kind of slowly faded out, and it's still growing a little bit, okay? So the point here is that the height depends upon the time, okay? You can't look at this one the other way. The time does not depend upon the height. Time just keeps going on. Okay. All right. I'll skip this one, see if you can figure out C, and I'm going to move on because this video is going to be way too long if I do every question. So again, please do C here. Try to get it. Try to see which one is the dependent and independent. Okay. Go ahead and read through this, and I'm going to do a few more examples down here. Okay. So here's our equation. Y equals 2x minus 5. And again, I'm going to try and complete, a few of these, trying to get the output. So if I input -2 into my equation, I'm going to get y equals 2 times -2 minus 5. That would be -4 minus 5 equals -9. So my output is the y would be -9. The ordered pair would be -2, comma, -9. Okay, now I'm just going to, let me erase this here, and I'm going to put in -1 as the input. Again, so that would be, get rid of that one. So -1 right here now it would be negative 2 minus 5 equals negative 7. And again, the ordered pair would be negative 1, negative 1, comma, negative 7. 0 would be, if I input a 0 here, I would just get negative 5, and then I would get 0 and negative 5. If I input a 1, I would get, well, let's see, 2 times 1 minus 5. That would give me negative 3. If I put a 2, 4 minus 5, negative 1. So then those pairs would be 1, comma, negative 3, 2, comma, negative 1. Okay, and now I'm going to put those, plot those on the diagram. Negative 2, negative 9 is the first one. Negative 2. Again, I always read the x variable first, so negative 2 is here, and the negative 9 would be down here. Okay, let me change my colors. Okay, negative 9. Next one is negative 7, negative 1, negative 7. So negative 1 is here, negative 7. And then 0 and negative 5, and then 1 and negative 3, and then 2 and negative 1. Okay, so there we go. I got my ordered pairs on the grid. Connect the points. Connect the points on the grid and extend the line in both directions. So here I'm going to do my best straight line here. Okay, and it says to use the graph to determine. The reason I put arrows is just saying that this keeps going on forever on both sides. So like so, and again, it says here use the graph to determine the value of y when x is 6. So this is what's called, this is the nice thing about equations and you know, graphing them, is that I can now predict what y is going to be when x is 6. Well, where is x is 6? X equals 6 over here. Now, all you do is you just go up to the graph until you hit your line, and then once you hit your line, you go across to the y-axis and you read what the number is there, and that is clearly 5. So when x is y equals 5 when x equals 6. It says use the equation to determine the value of y when x equals 6. The equation is y equals 2x minus 5. Y equals 2x minus 5. Okay, so that was in D, that was a visual way of solving this. In E, they want us to use the equation, so I'm going to go ahead and input 6 for x minus 5, and that's 12 minus 5 is 7. 7 like this, okay? So clearly my visual estimation was pretty bad, and that's probably because my straight line wasn't very straight. If I made this straight, it should have been something like this. There we go. And now when I read it off the graph, I'll go up here all the way here and then across, and that's how we should have gotten 7. So my line wasn't very straight. That was why I got it wrong. Okay, so write the value of y when x is 6 in the table using the first blank space. Okay, I think we can all handle that one on our own. So x equals 6, y equals 7, 6 comma 7, and then okay, let's look at some of these harder ones. So use the graph to determine the value of x when y equals 3. So now I have to work backwards. Now they tell me the output, and I have to find out what the input is. So when y equals 3, that's over here. What is the x value? Well, I'm going to go over here, go down and find out what the x value is, and that's clearly 4 on my grid. So I'm going to put in 4. Again, complete the following. So this relation is called a linear relation because the graph of the relation is a straight line. Okay. All right. What you're going to see in the next one, and I'm not going to do this in the video because this is already a pretty long video, but I do want you to do example number 5 at home. It's the same as example number 4, except what you're going to get here is you're going to get some sort of a curved line. It might go this way, it might go this way. I'm not really sure, but I'm guessing it's going to look something like this when you graph all your points and connect the dots. Okay, so go ahead and do this one, and And I think that's it. So again, pretty important concepts here. So make sure you're reading through all the definitions and all the examples in the book. Okay. See you next time.